Okay, so we are continuing now section 13.3, fundamental theorem of line integrals. We're continuing talking about that, and I want to do another example with you. Let me give you a moment to copy this example down. Okay, so in this problem, we want to find the work done. We want to find, let me just move this down a little bit. All right, we want to find the work done by a conservative force field, okay, in moving a particle along a curve C given by the line segment going from the point 0 to -1 to the point 5, -1, 1. So, all right. They are telling you that this vector field is a conservative vector field. Now remember, you learned that if you have a two-dimensional vector field, there's criteria that will help you determine if that vector field is conservative or not. And of course, if the vector field is conservative, that's great because we can utilize the fundamental theorem of line integrals to compute the work that the particle does, or that the force field does, in moving the particle along the path. And in fact, the tight path that the particle makes from one point to another point doesn't matter. It doesn't matter what the path is. All that matters is, if in a conservative vector field, is the starting point and the ending point of the path. You've not now, for a three-dimensional vector field, you don't have criteria yet to help you determine if that vector field is conservative or not. But you will when we reach section 13.5. And we'll get to that tonight. But that section, there is criteria dealing with something called the curl of a vector field. There is criteria that will help us determine if a vector field is conservative. But right now, we're just going to take it on faith that this vector field here is conservative. And so, are there any questions before I move to the solution? Okay, and I'll make another comment too. So, of course, if you don't have a conservative vector field, you can still compute the work done by a vector field, moving a particle along a path. But what's involved then is finding parameterization for that path and using the definition of work in section 13.2. Okay, but we do have a conservative vector field here, and so we'll use the fundamental theorem of line integrals to help us compute the work. And so here we go. Since the vector field is conservative, we can find a potential function. Now, this potential function would be a function of x, y, and z, 3 variables, right? It has to be because you have a 3-dimensional vector field. So we're going to find a potential function such that the gradient of the function is equal to the vector field. That's the definition of a potential function f. The gradient of the function equals the vector field. And the procedure that we use to do this is analogous to what you've already learned for finding the potential function for a conservative vector field in 2-dimensional space. Right? So, all right. We already know, right, based on the vector field here. One moment here. So the y squared is your p function. 2x y plus e to the 3z power is q. And 3y times e to the 3z power is r. So, you know, our vector field f is equal to p times I. I mean, this is notation you've seen before, but our vector field f in shorthand notation is p times I plus q times j plus r times k. So the p, the component, the first component, p, we set equal to the partial derivative of f with respect to x. The second component, q, we set that equal to the partial derivative of f with respect to y. And the third component, r, we set equal to the partial derivative of f with respect to z. So those equations come by setting the gradient of the function equal to the vector field. And now we get 3 equations generated. Are there any questions up to this step right here? Let me give you a moment. All right, well, very good. So what we're going to do, I look at the easiest equation. And of the easiest of these 3 equations, 1, 2, and 3, the easiest one to me looks like to be the first one. So the partial derivative of f with respect to x is equal to y squared. So what I'm going to do, I want to learn about my potential function f. So I have to integrate the first equation with respect to x then. And if I do that, then my function f is equal to y squared x plus this auxiliary function g. But the auxiliary function g is a function, hold on here, let me just write it a little bit. Hold on, class, one moment. Sorry, give me one moment here. Gosh, I can't get this right. Hold on. Better, okay. So my potential function f here, it would equal y squared x based on integrating this equation 1 here. My potential function f is equal to y squared x plus this auxiliary function g that must be allowed to be a function of y and z. So it's not a function of y alone because we're working in 3 dimensions, okay? So it's a function of both variables y and z. And think about it, if you were to differentiate this function with respect to x, the derivative of the auxiliary function g with respect of y and z would just equal 0. So this potential function is true. But the potential function, of course, is not equal. Well, the potential function is not useful until we determine what this auxiliary function g is. So to do that, what would you recommend we do next? Here's my potential function f. Okay. What should I do to that potential function? Okay, well, Ellie, that's right. Differentiate that potential function with respect to y. So you notice that I'm numbering my equations. This is my 4th equation. And I do that because, you know, it helps me stay organized, right? If I'm organized and I make an error, then I can go back and follow my work better if I stay organized. So, okay, we're going to integrate the potential function f with respect to y. Let's go to the next page then. Are there any questions? Okay. Well, all right. So I rewrote my equation 4 down again. I'm going to differentiate equation 4 with respect to y. When I do that, that's going to give me then the partial derivative of f with respect to y equals 2 times y times x plus the partial derivative of g with respect to y. Now you notice I don't have, like for that equation 5 there, the partial derivative of g with respect to y, that's not equal to g prime of y z. It doesn't even make sense to say g prime of y, I'm sorry. The derivative of g with respect to y and z doesn't even make sense, right? G is a function of 2 variables. So therefore, if we're going to differentiate g with respect to y, we have a partial derivative of g with respect to y. So just be careful on your notation. Sometimes students, they'll write like g prime of y z, and that doesn't make sense. Okay, now if g were a function of y alone, then g prime of y would be okay. Are there any questions so far on step 5? Maybe give me a thumbs up if you're okay with this step 5, and we'll move forward. Okay, excellent. Thank you, everybody. Okay, thank you, Charles, Ellie, Madeline. Thank you. All right, well, moving forward then, what I'm going to do is I'm going to compare this equation 5 with the equation 2. Okay, so if I go back and look at equation 2 here, equation 2 was the partial derivative of f with respect to y equals 2 times x times y plus e to the 3z. Well, e to the 3z then is going to have to be equal, then if I go forward here, e, you know, based on the equation 5, e to the 3z power is going to have to be equal to the partial derivative of g with respect to y. Okay, and now that I know that, again, you know, in order to determine my potential function f, I have to figure out what that function g is, what that auxiliary function g is. So of course, well, I'm going to integrate that partial derivative of g with respect to y. I'm going to integrate it with respect to y. And so then the function g of y and z would equal e to the 3z times y plus this now new auxiliary function h of z. So it's like what you learned last week and what you did in the homework today for section 13.3. It's just you have an extra variable to worry about. Now you have h of z, okay? Because, well, yeah. If you differentiate this function g with respect to y, you would get back e to the 3z power. So now you know more about your potential function. Okay, your potential function f is equal to y squared x plus e to the 3z times y plus h of z. Are there any questions? Please let me know. All right, let me know when you're ready to move to the next page. Okay, very good. Let me see. I think Emma had a question here. Okay, where did I get, so Emma's asking, where did I get the equation 6 from? Equation 6. I'll show you again here. So what we have here in equation 5 is we know that the partial derivative of f with respect to y equals 2 times y times x plus the partial derivative of g with respect to y. Okay, we know that. But we also know when we set up our, when we set the gradient of the potential function equal to the vector field, we had a second equation. If you go back and look on the previous page, the second equation was equal to 2xy plus e to the 3z power. That was equation 2. Okay, Emma's good on that. All right. That was equation 2 from the previous page. And so setting then, you know, setting the equations equal to each other, we know then that the partial derivative of g with respect to y equals e to the 3z power. Okay, very good, Emma. All right. Well then, so now what we have to do is we have to learn about what this h of z function is. Okay, and you know what, if we go back to, you know, our original 3 equations here, which equation are we going to use to learn to help us find out what h of z is? Which equation, 1, 2, or 3, do we need to use? That's right, Ellie, and equation 3. And incidentally, equation 3 is the one that we haven't used yet, right? Okay, so we're going to make use of equation 3. Now, equation 3 makes a statement about the partial derivative of the function with respect to z. So then for equation 8, what are we going to do with equation 8 here? What are we going to do with that equation? What do we have to do? What operation? That's right, Charles. We have to take the partial derivative of the function f with respect to z. Okay, so we'll do that. We'll do that. Okay, and so, well, hold on here. One moment, class. One moment. One moment. Okay, so we go to the next page. I rewrote equation 8 there, and I do that just because it's helpful that it's on the same page. We're going to differentiate equation 8 with respect to z, and then that's going to get us equation 9. And this is the kind of organized work that I would want to see in your exam work, okay? All right. So we get this equation 9, and we'll compare equation 9 with equation 3. So equation 3, I think I have enough room to write it in that little space there. Equation 3, okay, said that the partial derivative of f with respect to z equals 3 times y times e to the 3z power. So if you compare equation 3 with equation 9, that means then that, you know, h prime of z would have to equal 0, and the antiderivative then, which would be h of z, would equal constant k. So you see h is a function of z only, so there's no y or x hanging around there. It's just, it's like calculus 1. You know, what's the antiderivative of 0? It's going to equal a constant k. And therefore now we've found our potential function. We found it completely. And it's absolutely amazing. You know, you'd think something would go wrong, right? When you compare your derivatives of your potential function to the first like 3 equations, but it'll never go wrong because the theory says nothing can't go wrong. You have a conservative vector field, so things will always work out. You'll always be able to find that potential function. And there it is. Are there any questions at all? All right, well, let me know when I can move to the next page. Now that we have our potential function, it's time to apply what special theorem? What special theorem? That has these initials, F, T, L, I Good, Juliana. Good, Ellie. Fundamental theorem of line integrals. Okay. So this kind of problem is no different than what you did in 13.3 for the first set of exercises. It's just now you're dealing with vector fields in 3 dimensions. Okay, well, if we're good, I'll move to the next page. Okay, Malik, very good. All right, so here's the fundamental theorem of line integrals. And again, the fundamental theorem of line integrals says that the integral of the gradient of a function, well, and I want to be a little more, I mean, this here, I mean, what does the fundamental theorem of line integrals say? It says that the line integral, this line integral, is equal to the difference of the function, potential function, evaluated at your initial and end points, your initial point and your end point. Okay. And you see the vector field F, in this case, was a conservative vector field, and so it was equal to the gradient of your potential function F. It only works for conservative vector fields, right? And you can be sure, you know, you have to be prepared on the exam for, you know, I mean, what you're computing work here, right? You're computing the work. But again, this kind of very cool way to compute the work only works for conservative vector fields. You'd have to use what you learned in section 13.2 to find the work when you have a non-conservative vector field. And that'll involve then the path that the particle takes in the field is going to be important, hence you'll need to get the parameterization. But we're good here. So the work done by our vector field F and moving a particle along the curve C, given by this line segment, is the work's worked out here. You see, I don't even need to worry about the parameterization for the line segment. I mean, you have a formula for parameterization for a line segment, okay, in chapter 13. But you don't need to worry about it because it doesn't matter what path, I mean, you know, the particle takes from the beginning point to the end point. It doesn't matter. It doesn't matter whether the, you know, path is a line segment or whether the, you know, the path is like this path. It doesn't matter. It doesn't matter. Hold on, I don't know why that did that. You know, point A to point B. Doesn't matter the path that the particle makes in going from A to B. The work will be the same because you have a conservative vector field. All right, so I show the work here, and the final work is going to be equal, the work is going to be equal to 5 minus e cubed minus 2e to the negative third power. That's the work that this vector field does in moving the particle along that line segment path from the point 0, 2, negative 1 to 5, negative 1, 1. let me ask you, based on this answer here, well, let me give you a moment to catch up. Hold on. Okay, so based on this answer here, 5 minus e cubed minus 2 times e to the negative third, is the work positive or negative? Does the work that this vector field does in moving the particle from the initial point to the end point, or the terminal point, is the work positive? I agree with Ian. It looks negative. It looks negative. So overall, Malik, actually the work doesn't have to be positive, because if the net work is negative, that means then if the net work is negative, as in this case, does that mean overall that the vector field helps the particle in moving from the initial point to the terminal point? Or does the vector field hinder the particle from moving from the initial point to the terminal point? What would it be? Helping or hindering overall? If the net work is negative, as in this case. Hinder. That's right. That's right, Malik. That's right, Ellie. So you can have negative work. Yeah, you can have negative work. Sure. Now, if they say, you know, find the volume of this solid, that can't be a negative answer, but the work can, the net value of the work can be positive, negative, zero. It depends on the vector field and the path. Well, it depends on the vector field. It depends on the vector field. You know, and in this case, where your initial and terminal points are. But no matter what path the particle takes going from the initial point to the terminal point, the net work, the overall, the net value of the work is going to be negative. Okay. Now in section 13.2, where you don't have conservative vector fields, there the type of path that the particle makes going from the initial point to the terminal point does influence the value of the work. Okay? So that's another reason why you need the parameterization is critical to find. That's incorporated, right, in finding the value of the work. So for section 13.2. All right, are there any questions at all here? How many are feeling reasonably good with this? Notice the count, those K's cancel out in the work. I mean, are there any questions? Charles, you're good? All right. Kino's good? Wonderful. Ellie's good? Excellent, excellent. Well, let me stop the recording.